Good afternoon. This is the recording review for laboratory exercise 7. There is actually two reviews or previews, and the first one is recorded by the company that produced some of the slides. Um, but since everything is contained within the lab exercise, I felt it necessary to go over some of the material that is not in the first recording. And so we'll do this, of course. Um, what we're going to look at today is the shoreline processes that we find in the ocean and how those affect what we're going to look at in terms of, excuse me, features and through the exercise. So there's a lot of information contained within the exercise. You can certainly access your lab manual and go look at the section on oceans if you feel that you need more information. Um, but I believe there's enough information in here to answer all of the questions that you need. So it covers a lot of different areas, but all related to shoreline processes. So we'll just begin. And what I don't cover here is what you can easily get from just reading the exercise. I'm going to hit basically the highlights. The first paragraph is going to tell you that the ocean surface is influenced by three types of motion. And these are the waves, the tides, and the surface currents. And of course, these are what we're going to look at. Most of the shorelines on Earth are somehow affected by waves. Tidal action covers about 17%. And then currents, such as the Gulf Stream, only about 3%. So in order to understand how waves work, I have included a diagram here that has all of the A, B, C through E, which are discussed up here. And you'll want to look at that. And so this is called the anatomy of a wave. And it includes things like the crest here, wavelength here. That's the height between two crests. The trough tells you the wave height. Get that? This is the trough over here. And then we can measure the difference between these two. And that gives you the actual height of the wave. Then A down here is talking about the wave depth or the effectiveness of a wave as it moves through the ocean. And all of the energy in those waves is input by wind. So the wind has, of course, varying speeds of travel and can interject varying amounts of energy into the water. The faster the wind, the more energy it's going to transfer into the water. And so the waves are going to get larger. But as you get away from the surface, the wave energy decreases as you go down in this direction. And that is controlled by a simple equation. So the wave depth here is a function of the calculation of 1/2 of the wavelength. So in this case, we have a wavelength here of B. So one way to look at that is you divide B by 2, and that gives you the wavelength. So if the difference, the wavelength from this wave here to this one was 30 feet, then this depth from here to here, where the waves are affecting the water below the surface, would be 15 feet. 2 divided into 30. So most shorelines have irregularities. That is, they have areas that jut out into the ocean and areas that are behind that. So we call these, the areas that jut out, we call these headlands. And the ones off to each side that don't do that, uh, we call bays. So these are the indentations in the shoreline. And that's what's shown here in figure 2, with the headland being here and bays being here and over here. So this area here is an area of erosion. This area here and here where the beaches are areas of deposition. So what controls the erosion and deposition is a thing called wave refraction. And so these are contours that you see around here. This is 10 feet, wraps around over here, 20 feet, 30 feet, 40 feet, 50 feet. And it shows the advancing wave crest here before it reaches the ocean floor. And of course, that ocean floor, or reaching that ocean floor, is dependent upon the wavelength, or one half the wavelength, or the wave depth. So depending on how much energy the system has, it will reach it at different points. In this case, it reaches it at about 50 feet. Well, if that's the case, then the wave length, let's call it WL, for this system is going to be 100 feet, because half of that is going to be 50 feet. So since the waves are reaching the bottom, these are subsurface contours along the bottom, since they're reaching that at 50 feet, then the wavelength would have to be 100 feet. And so as it does this, it starts to slow down here. And over here, the wave is speeding up. And over here, it's doing the same thing because they haven't yet reached the bottom. And so the wave wraps around the area as it's shown doing here, like the contours are. And it's eroding here, and it's carrying the material away from the headland and depositing on each side. So then you have some questions to answer about that. Then we also can alter passive margin shorelines. There are 2 types of fundamental shorelines in the United States and basically everywhere in the world, but we're just going to look at the US. So if it's a tectonically passive margin, that is no uplift, the margins will have low relief and have smooth, sandy beaches. So this is found on the east coast of the US, or the Atlantic coast, and the Gulf Coast. If it's tectonically active, meaning it's coming up relative to ocean surface, this would be the Pacific coast And the coastline has a rocky character because of the wave energy that impacts, and it moves the sand either offshore or into various areas where it's not accessible. So you won't find great beaches. Now, Southern California has good beaches because it's a different environment. It's not tectonically active. But from Northern California all the way up into Canada, it's an active coastline and it has a very rocky, abrupt looking character to it. So the wave refraction, which is affecting mostly the tectonically passive margins, um, the waves that come into the coastline don't come in perfectly, that is, straight on. They're going to come in at a slight angle for the most part. It has to do with both the wind and how the shoreline presents itself to what wind is coming in. And this creates what is called a longshore current. So what longshore currents do is they cause sand and everything else to move parallel to the shoreline. And this causes something called uh, beach drift. And as I put here, the takeaway from this is that sand on a beach is always moving. So if you look at figure 3A, the waves are coming in at an angle of about like this. And so they push the sand up onto the beach here. But once the sand is pushed up and the water starts to withdraw, it goes back what is called normal or 90 degrees to the run of the shoreline because gravity is what's pulling it back and it pulls it back in this direction. Then the next wave that comes up pushes it up in this direction and then back. And so it has this zigzag pattern. But overall, the net movement is in this direction. And so it's transferring sand all along the beach. If you run out of beach, then usually if there's enough sand, it will continue building in this direction. And this is called a spit. So we go from a beach to what is called a spit, which is an extension of the beach, if it can do that. And then this, if this is a bay sitting here, this will extend out into the bay. And you can see the direction. It's getting bent around like this. And so it forms this kind of feature. And so this is helpful for knowing, at least in the fossil record or the rock record, how things moved. So this might form a complete barrier across a bay, and that's called a bay mouth bar. Also, sometimes it's connected to or forms a barrier island. We have a lot of those along the Texas coast and along the southern part of the Atlantic coast. So I also want you to think about submergent coasts. This is also the East Coast and the Atlantic coast, Gulf Coast. And there we have the barrier islands and a number of other features. There's emergent coasts. These would be the tectonically active ones. And they produce wave-cut cliffs and wave-cut terrace because the wave action is the most important. And so I want you to use this information in this area coupled with what we've talked about up here to label the coasts down here in figure 4 and all of the features that you will need headlands, wave-cut platforms, deltas, estuaries, marine terraces, wave-cut cliffs, spits, sea stacks, tombolos, beaches, barrier islands, sea arches, and baymouth bars. Each of these terms has a definition with it, or you can go back and look in, if you need it, look in the lab manual. And if you need further clarification, use the internet. Uh, but remember that you won't have the internet on the quiz or the final exam. So if you're going to do that, be certain that you learn these features. Some features may appear more than once. So here you have the first one, and the first one is going to be as explained, I guess I didn't give it a thing. Um, the first one is going to be the passive one. So we'll put a P here. And you, you see the features are different from this one, which is, we'll put a TA here for tectonically active. And you can see the headlands and different features are forming out here. And it also shows you the submarine topography under here. You can see the submarine topography here is much flatter than it is here. So this is more irregular. And then this will evolve into this and have even more features. So you can look at those, read the descriptions, and find the features that are here. So we can look at section C talks about the modification of wave-dominated shorelines. And these are going to be typically, not always tectonically active. Some tectonically passive margins can certainly be dominated by waves. More on the Atlantic, the Gulf doesn't really have that big of waves. So on these wave-dominated shorelines, we can construct certain kinds of structures that are meant to trap sand on the side facing the longshore current. These are called groins. And so in this case, sand is being trapped over here. This is the groin here. And the problem with groins is behind it, you have no sand or very little sand. So sand that's moved in that direction, what there is, will eventually end up over here. Then in this case, there isn't anything, so there's nothing in this particular area. And here we have something called a breakwater, and this prevents the waves from hitting that beach, and so it develops behind it. And this is the whole thing behind jetties, groins. Jetties are like groins, except they protect the mouth of a bay and keep the bay from filling up with sand across here, which would be a bay mouth bar. Okay. So then you're asked a few questions about that. Figure 5, of course, is the one we just looked at up here. Figure 6 is the one below this, and it's asking you to look at figure 6A, which is the top map on the next page, and describe the difference between a groin and a breakwater. So this one has the groin here and the breakwater over here. This one, you can find the breakwater and the groin. And I just want to know if you know the difference between them. So then there's some questions down here that apply to figure 6B. That's the deposition or erosion of certain features, and you can go through that. And then you have to make some explanations. Section D is shoreline processes, and this has to do with tides. So tides are superimposed upon the wave system. They're controlled by the moon, its position relative to Earth, and also the sun, although the sun is significantly far further away than the moon. So the moon has a greater influence on Earth's tides than does the sun. So the sun produces what is called a solar tide, and the moon produces a lunar tide. Generally speaking, you either get one or two high tides a day, depending upon where you are. If everything was perfect, then the high tide would be 6 hours separate from the low tide. Low tide would then there'd be a high tide 6 hours after the low tide. So basically, you get a high tide every 12 hours and a low tide every 12 hours or every 6 hours, but it lasts for 12. So that's how it all works out if the moon was located at perfectly 90 degrees to your position. So the vertical distance or vertical difference in elevation between the high and low tide is referred to as the tidal range. And we'll show that down here. I'll come down to it in a moment. Then on coastal regions dominated by tides, we produce a unique type of landscape called a tidal flat. And that's what you see down here in this diagram. They'll have a tidal inlet. The tide rushes in through these, spreads out. There'll be a stream, of course, coming out when the tide is out. And right now the tide is out here. But when at high tide, it'll be back along here and it will cover that area. So this is on Coos Bay, Oregon. You can see all the various tidal. So here is figure 7, which diagrams the tide relative to Earth. So here we have high tide, and high tide is a maximum when the moon and the sun are aligned on one side, or when the moon is on the other side over here, and the sun is on this side. You also have high tides. So you'll have a high tide here and a high tide here, a low tide here, and a low tide down here. When the moon is in its quarters, that is 90 degrees to the sun, you still get a high tide, but the high tide, of course, the maximum high tide is following the moon. So the low tide is over here, so you get a lower high tide and a higher low tide when the moon is in the quarter here and here. And here you get a much lower low tide and a much higher high tide. So this diagram that I've given you here is basically the variation in tides over a 30-day period. So from April 1 to April 30th. This is the feet in range of the tides. And in this case, you have a low tide here, a high tide here, and a low tide here, and you were working on a high tide over here. So here you have two low, high, and two really high tides per day. So here's one and two, and this one uh, should also have another higher. So we have low tides here and a high tide here, but one is higher than the other because of where the moon and the sun are. Um, so you can see the variation that you have in tidal ranges. And at this point, where this is much greater, it means that you're dealing with this kind of situation. And where there's less of a range through here, you're dealing with this situation. So that's what this diagram is also showing you. It's talking about the Earth, Moon, and Sun associated with what are called spring and neap tides. So when it's in this position with the first quarter here and the third quarter over here, they're not aligned. This is called the neap tide. And the high tide situation is called the spring tide. So in this case, this would be the spring tide, and this one down here would be the neap tide. So there's a number of questions associated with that, which you can get out of the diagram or out of this preview. We haven't yet talked about diurnal tides, semi-diurnal tides, and mixed tides. So a diurnal tide is a daily tide, one high tide, one low tide. Semi-diurnal is twice daily, so you have two high tides and two low tides. Mixed tides look much like semi-diurnal, but they have usually very high water heights and very low water heights. So in this case, along the east coast of the U.S. here, the Atlantic coast, we have semi-diurnal tidal patterns. And remember this is 24 hours from here to here. So there's high, high, low, and low. For most of the Gulf Coast, we have a diurnal, which has one high tide and one low tide every 24 hours. Along the Pacific coast and parts of the Caribbean coast, we have mixed tides where we have very high tides here and here. We have very low tides here. We have a lesser high tide here and a lesser low tide or higher low tide, if you want, there. So that's why they're called mixed. There's also a video that goes with this. It's assigned. I would very much like for you to look at this and get the information out of it so you can properly answer these questions. 19 refers to the following figure 11, and it asks you to classify each of the tidal patterns shown in the diurnal, semi-diurnal, and mixed tides and where they occur. So you would be expected to look at San Francisco, Boston, and area of China and put those three in each of those in these. And so that is the lab assignment. So I hope the preview helps you, and see you next time. Have a great day.